All right, welcome back, chemists. Yesterday we finished up with symbolizing atoms, and we had not mentioned one thing on the bottom of that slide, which is isotopes. So, isotopes are elements that have, well, atoms that have the same number of protons, but a different number of neutrons. So chemically they behave the same, but their mass is slightly different. So on the next page, I'm going to give you some examples of different isotopes. So I'm looking for an atom that has 12 protons and 13 neutrons. So instead of crowdsourcing this answer, if you're at home, you take out your periodic table. I'm modeling it for those of you who are at home. I'm modeling it right now. Take out your periodic table. You think to yourself, okay, 12 protons. That's the atomic number. So I'm looking at magnesium. Magnesium. And I know the mass of an atom is centralized in its nucleus. And I know each proton and each neutron has an atomic mass, or a mass of one atomic mass unit, 1 AMU. So I add these two numbers together, 12 and 13. The mass of this magnesium isotope is 25. So that would be my symbol here. Okay, for the next two. These are two different isotopes of oxygen. I have oxygen 16 and oxygen 17. So oxygen 16, I go back to my periodic table. You'll end up memorizing a lot of these. I'm not asking you to memorize, but just because we use some of them so frequently, you'll memorize them. We know oxygen has 8 protons. So we know the total mass of this oxygen atom is 16 AMUs. So if the total mass is 16, 8 comes from the protons. How many neutrons must I have? 8. So for oxygen 17, again, we know it's oxygen, so it must have 8 protons. Now, if you don't want to do the tricky math of 17 minus 8, you can just go, oh, it's got one more atomic mass unit, so it must have one more neutron, so it must be 9. Or, you can go through the arduous math of 17 minus 8 to determine how many neutrons there are. You'll also see this written, sometimes you'll see this written like this. So, especially when you're reading, maybe not scientific literature, but if you're reading literature about science, with the Manhattan Project, you'll oftentimes see the isotopes written out with their name and then a dash and their mass number. So these two things, those of you at home, I just said these two things and pointed to two things. You couldn't see what I was pointing to. These two things are equivalent. Okay. So now at your tables, figure out what is the symbol that you would put down here. At home, please do the same. You can talk about it at your table or to yourself. Okay, so you guys should have gotten uranium-238. This is, if you look over at your periodic tables, you'll see that's the most common isotope of uranium. Uranium was also used where? Atomic bomb. Uranium was used in the atomic bomb. It's also used in a lot of nuclear power plants. This is a very common isotope. You also see uranium-235 used frequently. That's the one that you can enrich. I believe that's the one you can enrich to get power and weapons from. But you should be very comfortable doing this and going back and forth between symbol and protons and neutrons. Okay. Average atomic mass versus mass number. what I showed you on the last slide is that oxygen, you can have oxygen 16 or oxygen 17. Each element comes in various isotopic flavors. That means there are different numbers of isotopes of each element. Some have only one that's stable, some have none that are stable. Those are the radioactive elements. Some might have a lot that are stable. So let's look at one example. There are two naturally occurring isotopes of lithium, lithium-6 and lithium-7. So where does the average atomic mass on the periodic table come from? So what they do is they take a representative sample, a huge sample of lithium, and they say, well, let's measure how many are lithium-6, measure percentage that are 6 lithium, and percentage that are 7 lithium. And then you do what's called a weighted average. So you look at percentage. What another way we state this is relative abundance. So you look at the relative abundance of each isotope, and then you can do a weighted average, and we'll practice this in a second. Yeah. So the question came, how do you measure 1 AMU? We're actually going to get to that in a couple of slides when we talk about mass spectrometry. But that's an awesome question because it's not something that we can really readily measure in our labs here. Yeah. Okay. So if we had 50% lithium-6 and 50% lithium-7, we would expect our average atomic mass of lithium to be 6.5. It's not. It's 6.94. So in nature, which has a higher relative abundance? Lithium-6 or lithium-7? Lithium-7, right? It's closer to the average. Now, how about chlorine? If I ask you what is the most abundant isotope of chlorine? Take a minute, think to yourself, look on your periodic table. What is the most abundant isotope of chlorine? Do you want to answer that? No. I wanted you to look on your periodic table and figure it out. Okay, I'm actually going to pull from the deck for this. This is a rare instance when I can do that. Don't be afraid to be wrong. Rudy. Most abundant isotope of chlorine. So what's the 35? And there's a link here for web elements and isotopes. It's a great reference. Yeah. So the question came, can we always do that to find most abundant? Is that sort of what you're getting at? Mm. So chlorine's actually a good example of what the question was. If they have, for example, potassium, I don't know this off the top of my head, but I think the two naturally occurring ones might be potassium 39 and potassium 41. I think you're right. But it's still much closer to 39. But so chlorine is another example. There's chlorine 35 and chlorine 37. That's the other naturally occurring isotope. It's not 36. It happens to fall much closer to the most common one. And there are probably, I'm not sure off the top of my head, but there are probably some instances, especially when you get up to some of the higher atomic weights, where they have lots of isotopes, where the most abundant isn't just rounding off the atomic mass, but 95, 98% of the time. That's the way you'll think of most abundant. Unless I'm going to show you when we get to mass spectrometry a way to totally figure it out. For sure. Okay, so the web elements is a great place to find out info about isotopes. You might get problem set questions that require you to look up information about isotopes. This would be a good place to go. Okay. I think we skipped a slide. We skipped a math slide. Oh, look at that. I did this out before, and I didn't remember that we actually used potassium-39 and potassium-41. So there are two naturally occurring isotopes of potassium, as I mentioned mere moments ago, 39 and 41. How do we find their relative abundances? What percentage of the naturally occurring isotopes are 39? And what percentage is 41? Okay. So because we're running a little short on time, I'm going to walk you through this. It's two equations, two unknowns. Yay, we're going to algebra. Okay? So, two equations, two unknowns. I know that my fraction of potassium-39 and my fraction of potassium-41 has to equal 1. All right? So, x equals 39k, y equals 41. And I know the average of all potassium atoms in the known universe, measured by a small sample taken on Earth, is 39 point, we'll round it off, 39.1. Just as an aside, a lot of people came to me with questions about significant figures in the problem set. You'll find neither Mr. Hamill nor I are huge sticklers of significant figures until we get to the point that we teach them to you, and then you can worry about it. But for the time being, don't worry so much about significant figures. We'll get there. So I know that the average of 39 and 41 is not 39.1, right? So what I do is called the weighted average. So I take x times 39 plus y times 41. Yeah, the question was over 100, like, do you need to put it over 100? If you do it in percents, you do need to do it over 100. But I like to use decimals because you don't have to make that extra step. Okay? So, how about at your desk, take a minute, try to solve for x and y. This is just good little practice. At home, I suggest you do the same. Don't skip ahead. Don't fast forward. Do the work. Maybe even press pause. I think some people are trying to use solver or use their graphing calculator to do equations to unknowns, which is fine. I have no problem with that. Use your resources. Okay. Oh, we have a random question. So the question was, how can you know that you have a certain amount of 39 and a certain amount of 41 as we're doing the math here, if we're in a given sample? Mm-hmm. So if you take a big enough sample over multiple places of the Earth and you test it and it comes out about the same, you can figure that the universe is going to have a similar distribution. It could be different. So on Earth, these all hold true for all the testing we've done. Right. Right. We may find out that there's very different physical constants throughout in different areas of the universe. But as far as we're concerned, 39.1. Yeah. The question was, for normal non-radioactive isotopes, are there only 2 isotopes? No, you'll get some that have a huge number. Some that have like 7 or 8. Where I'm not going to give you 7 equations and 7 unknowns. You'll get like the 2. You might, a way it might be though, I could give you 3 or 4, but I would give you the abundances, and then you would just plug it into this second equation because you would know x, y, and z, and you wouldn't be solving for x, y, or z. you'd be solving for the average, right? Okay, so what do we get? What percentage is 39? Just shout, Rebecca. 95%. And by process of elimination, this must be 5. One of the skills that I want you guys to build over the course of the year, and this is something like, I don't know, maybe it's not all that useful, but I find it kind of useful, and it's sort of like a cool, like, it makes you seem a lot smarter than you might actually be if you can do this. I want you to be able to look at this set of equations like this and be able to solve it immediately. Being able to do quick mental math, even though it's not that tricky, it comes with practice, makes you seem a lot smarter, right? So you could look at this immediately and say, oh, I have 39 and 41. I know I have 39.1, which is only 5% of the way from 39 to 41. So immediately you must know it's only 5% of the way. So I know 95% of what I have has to be 39. 5% of what I have has to be 41. I don't expect you to be there now. You might not get there over the course of the year. But if you can like practice doing this sort of quick mental math, it helps you. One of the things that we're going to find on our upcoming test in like a week and a half, or no, the 27th, whenever that is, 2.5 weeks, is timing is what's going to throw most people off. You might know all the things, but you're really crunched for time. Like, it goes fast. The 55 minutes goes super fast. So the quicker you can do some of these things in your head, the better off you'll be taking the exam. Right. Okay, so you guys got this, 95 and 5. So why does the nucleus stay together? There is a balance between two forces. Right, we look at a nucleus, we say, oh my gosh, we have all these positively charged protons, and we have all these neutrons. Why the heck are these positive things sticking together? If you looked at a nucleus without a good understanding of chemistry, you'd think like it would just blow apart. So the last thing we're going to do, we have about a minute left. We have a balance between the electrostatic force and the strong force. You also sometimes hear it called the strong nuclear force. So these two forces are balancing each other in the nucleus. And if they're in balance, you get a stable nuclei. So electrostatics is relatively strong, especially compared to gravity. Gravity is very weak compared to electrostatics. But, as the name implies, the strong force is extremely strong. And because I don't necessarily like to use descriptors when I can use numbers, it's about 100 times stronger than the electrostatic force. So we have this strong force, and you don't need to know this, but it's based on the quarks that make up the protons and neutrons. So protons and neutrons can be further subdivided into quarks with up or down spins, and that's sort of what that's what causes the strong force. You don't need to know it. You just need to know that there is a strong force that exists that holds the nucleus together. Super strong. Electrostatics works over a relatively long distance. Wow, that came out awesome. Long distance. The thing about the strong force and why it doesn't just suck all of the protons and neutrons in the universe together into one thing is that it only works over very short distances. We're talking about approximately the size of the nucleus. Which is why it's so hard to have a nuclear reaction. Because you have these electrostatic forces that act over a long distance. So as you get two protons that start coming together, they feel the electrostatic force at a long distance. So they repel each other right away. Now, if you shoot a proton at the nucleus with enough energy that it can overcome this electrostatic force and come right next to another proton or neutron, the strong force takes over and it sticks together. Okay. We'll talk about this more tomorrow. we'll talk about it more tomorrow. Grab problem set 2 on your way out the door. You might want to just start looking it over. I'm here after school today and tomorrow. Okay. Do you need this notebook back?
No. It's just for this class. I'm just using it.
Why don't you just pull the page out and staple it.